Hello class, today we're on lesson number 4 in our chapter 7 of simultaneous equations, and we're going to be graphing simultaneous equations. And again, this is something that you've already done, but we're applying math as we keep doing over and over. We learn something and we apply it. We apply it into a different arena of knowledge. And now that you've learned what these simultaneous equations are, or how to at least solve them by subtracting and adding, we should just roll it back and go to our previous chapter, and we know that we can certainly graph an equation, and these are these two variable equations with x and y, and we understand how when we graph them, they form a lines or straight lines that in this particular case we're going to notice that when these lines intercept, when they intercept, we're actually finding what we're looking for when we're solving for simultaneous equations, which is basically the answer for both. So let's go ahead and start reading. Well, we have first our comic strip at the top, our illustration. It says, "Whiz, I need a potion to help me win the next race." And so he starts thinking. He says, "This stuff will give you the speed of a greyhound." And he comes back. He's all beaten up. He says, "What happened?" He said, "Well, I was out in front by 30 yards when I spotted a cat in the bleachers, so I guess it worked too well. He acted like a greyhound, started chasing a cat." Now, suppose that a greyhound spots a cat 30 meters away. If the greyhound runs towards the cat at a speed of 15 meters per second and the cat runs away at a speed of 10 meters per second, how long will it take the greyhound to catch up with the cat? Now let's just pause for a minute and let's take a look at this from a linear standpoint. We've done these problems, and if we were to say here is the greyhound, all right, this is the point where the greyhound is. Let's put a G. And now the greyhound spots the cat, and here's the cat, all right, and it's 30 meters away. So from here to here, we know is already 30 meters, right? And the cat is running at a speed of 10 meters per second, right? So there's going to be a point over here, right, where the cat and the greyhound both meet, all right? The cat and the greyhound are going to meet. Now we also know that the greyhound is traveling at what speed? He's traveling at 15 meters per second. I'm sorry, 15 meters per second. All right, so 15 times x. X is going to represent time. How long will he run? And remember, he's running from here to here, right? All right, so he's running at 15x, and we know that the cat is going to be running at 10 meters per second. So we know from our when we solved problems before that we can actually create an equation out of these things. Now, what we're trying to do here is we're not necessarily taking that approach. We're going to look at this in terms of a graph, and we understand that, for instance, that the cat, is equal to, y is equal to, well, actually, let's start with the greyhound, and y is equal to 15x. So what is y? Well, y is going to be the time, or excuse me, the distance that they travel, because we're going to multiply meters per second times the amount of time. So this is actually going to be the distance. And we also know that y is equal to 10x plus 30. Not 30 m. No, it's 30 meters. But so this was helpful to help us create our equations, and we know that actually y is the y here. That's the same y, right? It's the same distance that they're covering. So I'm kind of looking at this from a different angle from information that you've learned before. But If we just simply follow the book, this is one way to answer this question is with a graph. If a greyhound travels at a rate of 15 meters per second, the distances it covers in different times are given in this table. And we see 1, 2, 3, 4, and we could see that the distance is 15, 30, 45, and 60, and so forth. In which x is the time in seconds and y is the distance in meter. Now, a graph corresponding to this table is shown at the top left, and we see the graph up here. Its equation, we see y is equal to 15. So let's look at the first one. We see the greyhound, and we see this line shooting straight up, and we see that the x-axis is time. Okay, it's in seconds. So for every second, there's a certain amount of meters. We see the y. So we have these graphs that show us that as time goes forward, the distance gets further. Okay, it's not really, don't look at that simply as what we're looking here. I am giving you a different way of looking at it so that you can understand how these two correlate. Now, if the cat runs at a rate of 10 meters per second and starts out 30 meters ahead of the greyhound, its distance from the point at which the greyhound begins the chase are given in a table. Now, we know at 0 seconds he was already 30 meters ahead. Okay, kind of like that amaryllis plant that we had. Okay, the y-intercept is really a value. It's not just 0 because it's not starting at 0. It has a value of 30. So he's actually starting all the way up at 30. Now, the second graph corresponds to this table to its equation y is equal to 30 plus 10x. And we can see that, excuse me, in fact, we would we would be able to combine these two graphs and see where they actually intersect each other. Now, to find out when and where the greyhound catches up to the cat, we can draw the distance-time graphs of both animals on one pair of axes, and this has been done in the third graph, which shows that the lines intersect in the point 690. The coordinates of this point are shown, or the coordinates of this point are the solution to the simultaneous equations y is equal to 15x and y is equal to 30 plus 10x. Okay, if the greyhound catches up with the cat in 6 seconds at a spot 90 meters from where the greyhound started, so we know that this is the point where they're going to intersect. That's where the greyhound catches up to the cat. Now, this problem illustrates a way to picture the solution of a pair of simultaneous equations. The graph of an equation in two variables consists of those points whose coordinates are solutions to the equation. This means if two equations are graphed on one pair of axes, their common solution consists of coordinates of a point or points that are on both graphs. In other words, the point or the points in which the graph intersects. Okay, so if we just sort of look back over here, I'm showing you this from the word problem. Remember, we could have written this differently. We could have said 15x is equal to, we had 15x, and we've done this before, all right, is equal to 10x plus 30. We did these with word problems. The point where the greyhound is running, and this is more of an illustration of the distance on the ground. The cat started here, but at this particular point is where the cat catches up to, or rather the greyhound catches up to the cat. Now we're using graphs, and when we graph the first one, we're able to determine that at point 0 we see that the greyhound ran, and this was that's his equation over here, because we know that this distance, we would have called it d, but let's say y is equal to 15x. We're just going to use the variable y, right? And if we were to graph the second one, and we know again that y is equal to 10x plus 30, because or 30 plus 10x as they write it, which means that we start off at 30, and again there's a slope is slightly less. We see that the rate of each is different. So the greyhound's going much faster. His slope is going to be slightly more inclined than the cat. And ultimately what happens is that they put these two together. okay? And they're able to say, well, if this is the greyhound and if this is the cat, then at what point do they intersect? And if we were to draw our graphs into proper scale and make sure that we're as very detailed as we should be, we will see that after 6 seconds and 90 meters, they both intersect. And that would be the answer to the simultaneous equation. So we didn't necessarily have to add and subtract them. We could have graphed them. And we also have some examples over here. We have example number 1. We have equations x plus y is equal to 6 and y is equal to 2x. Solutions that are pairs of positive integers are shown in the graph below. So we see these. We have 1, 5, 2, 4, 3, 3, 4, 2, 5, 1. And then we see on the other one going upward, 1, 2, 2, 4, 3, 6. So the question is, what's the answer, or where do they cross? Where do they intersect? Well, if we were to take these two graphs and put them on top of each other, we will see that 2, 4 is the point where they intersect, okay? And we can see here that when you put in 2 and 4 into either of the two equations, they are actually true. So now we also have another one. Find the solution of simultaneous equations. We have x plus 4y is equal to 8. And we have y is equal to 1/2 x plus 5. Now, 1/2 x plus 5. Now, graphing, we've learned methods of graphing, and we could sit there and create these tables, or we know that we can go with that slope-intercept. And I think that's really the trick to doing this work, is to really figure out what's the easiest way to graph these things. Because you have to graph them, and you have to graph them accurately. Otherwise, if you're getting the wrong angle, you have to find where they actually intersect. And if you're very accurate in putting your points down, and you're accurate in drawing your line, again, I just do these here on the screen. Please don't try to hand draw. You should be using a straight ruler on your graph and just match those points as properly or as accurately as possible, and use a nice sharp pencil. You'll see that these points are going to go directly through intersections of intersections of these whole numbers. At some point they're really fractional. If we were to just take a look at the answer to this particular one, example number 2, notice how when you're looking at the x-axis and you see how from 0 to 5, notice how x plus 4y is equal to 8. Notice how it's just cutting through in between lines, but notice how it just cuts right through that one point on the y-axis, okay, at 2. And notice how the other one, y is equal to 1/2 x plus 5, it's just cutting right through the 5 at the y-axis. So, and there's a reason for that, because we know that if we actually solve these to find their y-intercepts and their slopes, we would have known that those points are right there, right in front of us. We see that in the very beginning. They say to graph the first equation, you can find its x and y-intercepts. Okay, that would have been the easier way, maybe. Well, what's the x, and if x is equal to 0, well, y is equal to what? 2. And if y is equal to 0, then x is equal to 8. Okay, so we found the x and y intercepts for the first one. And the second one is already in the form of a slope-intercept. That's y is equal to ax plus b. So we know that a is equal to 1/2. That's the slope. B is 5, that's the y-intercept. So there's a reason why these graphs are drawn the way they are. You could just see those answers hidden inside of the equation. Of course, it takes a little bit of math, and it also just takes a little bit of getting used to, and that's why you do your homework, obviously. So we can see now that if you draw these lines and you draw them accurately, you're going to see that both of these lines intersect at -4, 3. Okay, if you didn't draw them accurately, that -4 might have been closer to -3, or the 3 might have been closer to 4, and it just wouldn't have given you the right answer. So you really should be You should, in fact, most of these answers I'm sure are going to give you whole numbers. If you're ending up somewhere in between, you might want to double check it because it's maybe that you just didn't draw your line as accurately as possible. And that's something we learned again in the previous lessons and previous chapters. So that is the end of lesson number 4.